Yes. The third time is the charm. We've got 5 by 5. So let's restart once more. It only took us 7 minutes. All right, so, hey guys, what's going on? Memes here. So, first things first, after boomering this twice, thank you, Poindexter, for pointing out that I'm just rambling off to myself here. We'd like to wish a swift recovery to Rick DeWitt. Believe he may have had a procedure recently, but he's a fighter and an absolute mad lad in my opinion. So swift recoveries to you, my friend. Okay, so after multiple boomerangs, let's get into what the heck we're actually talking about. Yes, we're doing a do-over. I have to take 2 mulligans. See, that's one of the things I noticed. They say, "Oh, don't make the same mistake twice." I find that I do make the same mistake twice. But the third time is just like in Monty Python, the Holy Grail. It's like, all right, they said you couldn't build a castle in a swamp, but we did it anyway. That one sank into the swamp. So we did it again. That one burned down, fell over, and then sank into the swamp. But the third castle stood. And that was the castle that Lancelot basically went complete He-Man and seemed to commit a lot of very unnecessary atrocities to people. But hey, it's Monty Python the Holy Grail, so I guess comedy allows it. Okay. So at least we had a little humor because you gotta laugh at somebody. If you can't laugh at yourself, I mean, come on. All right. So for those of you that may have seen the thumbnail here, that we have this thingy over here. What the heck is this stuff over here? Okay. So the claim is, if you've watched some of the previous videos at all, we've conjectured that there is a mass bank to universe. What the heck am I talking about? So basically, what we did is, and again, this is conjecture here. This is conjecture. Let's play Wolfram again, so we can totally.
Turtles all the way down.
That was the incorrect clip. Let's play the correct one. Where was it? Okay. All right. Buckle up, my friends, as we're going to conjecture.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
There's people are commenting on the outrage of hacking the universe on a MacBook Air.
All right. So the stream title is a series of remarkable coincidences or coincidences. One of those is the technical term. Okay. So what we have over here is I claim, is a mass energy bank of universe. Why? Because I believe it was Julian Barbour that said that on his tombstone, he does not want pepperoni and cheese. He wants nothing but ratios, because that's his whole big thing. Because these ratios between different stuff doing different things within our realm of persistence lead to basically reality as we know it here. Okay. How the heck do I get this number? It's 7.488 times 10 to the 78 joules. What the heck is even that? Okay. So we're following at least the concept of maximal extendability. And what is that? No arbitrary boundaries. Essentially, if you're going to assume that we can continue to go down smaller and smaller and smaller, and we can do that infinitely, well, then by extension, you're going to say, well, if we can go down infinitely, then things will just get bigger infinitely. Okay. I mean, that's a logical framework. Personally, I happen to believe that there might be a limit to space as we know it, or at least that we could calculate. Now, we might not necessarily be able to observe that on our meterish level or something like that, but perhaps we could in the future. Okay. So the whole claim is that we're taking that thingy over here. What is this thingy? We're taking our reference length, the meter, that we have for our coherent system of units. And again, a coherent system of units follows these 3 little thingies here. FEP, FEP. What the heck is that? F equals ma. You may have heard of that. That's force equals mass times acceleration. Okay. And then energy equals force times distance. It's that force used to move something a particular distance, and that's energy. Okay. Now, you also have power, which is energy divided by time. So basically, your computer, or at least my computer right now, it's using energy. Now, if I unplug my computer, one, it's probably not going to do as well. But number two, it's then going to have a limited amount of power that it can run for a duration of time. See, energy divided by time over here. And then it will power off because it will be out of power. Okay. So that's a coherent set of units. So the claim is that if we had some logical way, and again, could be completely wrong, if we had some logical way to calculate how much mass, energy type stuff could be in universe. Okay. So the claim is if you happen to take this ratio of 1 meter, our reference of length, divided by the minimum of length, the Planck length, and we have that ratio, and then we square it because, well, we like doing that in physics. I think Professor Carroll had a video at one point in the Biggest Ideas of the Universe series where he's like, well, in physics, we like to look at the relationship between different things, and sometimes if that doesn't make sense, then we square the result, and we can see if we can interpret it. So I'm like, that's cool, let me do that. And then the interesting thing is, when you do that, you get your giant number. You're like 3 times 10 to the 69. Ginormous number. Now, if we take that ginormous number and then we multiply it by the base of mass, the Planck mass over here, okay, if we take that, we're going to get still a really big number, but that's the negative 8 power. So you basically knock off 8 of the exponents. So you get that 10 to the 61 kilograms. It's about 8 times the magnitude of the estimated total mass stuff in the universe. Okay. So that's going to be important. So basically about 100 million times more than what we can see in the observable universe. Okay. So if we take that, and since mass can be converted to energy via good old Albert Einstein, E equals mc squared, and that's a big number. That's already got like 16 orders of magnitude, or basically you throw an extra 16 zeros after something. Basically, you're going to go from like 10 to the 69 to that 10 to the 61 kilograms. Excuse me, I'm doing that wrong. We already said that part. If you're taking that 10 to the 61 kilograms and you turn that into energy, you're going to get this number here. That 7.488 times 10 to the 78 joules. I am saying the digits as well because this is important. Why? Because if we go a little bit over, you're going to see I wrote down this thing called the Planck spring constant. And if we notice, it happens to have the first beginning digit, 7.488, times 10 to the 78. Seems to be the same number. The dimensions are different. That's kilograms divided by seconds squared. Why? Okay, so now this is something probably a first-year physics student could actually explain better than I could, because again, I haven't ever finished a full official physics class. We're going to start to go through, I think, some of the MIT lectures and stuff, and then Thad's going to actually start like doing some, basically helping to teach me and do some elementary classical physics and stuff like that, just because that's useful stuff and it's fun. It's fun, actually, learning different things. And especially if you happen to have an online calculator like Wolfram Alpha that does a lot of the hard stuff for you, but at least getting the concepts down so we can try to figure out what the heck's going on. Okay, so the spring constant, it has something to do with if you've actually done physics, and basically if you have a spring, an idealized spring against a wall, it's on a block of mass. Okay, now we throw out friction and all that other jazz. We're assuming there's no friction or anything because we want an easy calculation. So basically, if you tweak that mass and it's going to start to oscillate, it's like, oh, it's kind of like a harmonic oscillator. So the spring constant, its dimensions, as we can see, it's kilograms divided by seconds squared. Okay. How the heck do I know this? It's because Wolfram Alpha told me, and a lot of times it's people like to go down wiki holes. I often go down Wolfram holes, in that you never know where you're going to. Basically, it's a computational database that Stephen Wolfram is an absolute mad lad, in my opinion. Finally, actually created the thing that he had conceptualized when he was like 10 or 12 years old. It's like, well, we have computers, we have a bunch of information. Well, what if we use computers that had that information that could compute that information? It sounds like, oh, there's no reason why you can't do this. That might be true. Now, actually pulling it off is a whole different ballgame, because if anybody's ever done programming, there's a lot that can go wrong. Okay. Poindexter is saying that I think we're in a closed system. I'm very sympathetic. I'm basically kind of claiming the same thing, that we're basically in an N hypersphere of maximal volume. And we can go through the reasons for that maybe at the end, if not, maybe another day. Okay. So, but what the heck is a spring constant? Okay. So the only reason I know this is because a lot of times you'll see different Planck units. Like you're going to see our friends, you'll see very often the Planck length, the Planck mass, the Planck time, the Planck temperature, and sometimes you'll even see the Planck charge pop up. Okay. So the claim is those are bases of reality, aka they're important things. Why? Well, because from those units you can create, at least to first level approximation, most of the constants of nature. So at least some of the most important ones that I don't think many people would argue about. So let's do this right here. Okay. So the claim is we have this thingy right here. Okay. So let's do this. Okay, so we have our reference of length, the meter, because we're using a coherent system, divided by a minimum of length, and we're squaring it. All right, it gets us that 3 times 10 to the 69 number there. Okay. Now, we toss in the Planck mass. It's got a magnitude of 10 to the minus 8, so the exponent's going to go down by about 8. So I get, 10 to the 61 kilograms. And then, by the magic of E equals mc squared, I just raise it to c squared, the speed of light squared. And then we get this number here. So that's where that number comes from. Okay. So now where the heck does the Planck spring constant come from? Now, a lot of this, I think I was just multiplying and dividing different things, just playing around, going down a Wolfram hole, and then you come across something like this. What's this? All it is the Planck mass divided by the Planck time squared. And I would see this number, and I have no idea what the heck this number is. Kilograms per second squared. I didn't need to know, because Wolfram alpha tells me, it's a spring constant. Huh. Now you can go through more. You could say it's a spring constant, a force gradient, stiffness, surface tension, Peel stress, spectral radiant energy, density with respect to wave number or cleavage. Okay, so those are interpretations of this thing here. So I'm like, spring constant. Wait, it's a spring constant. That's usually something you figure out when you have like a mass attached to it. This happens to be a mass energy that happens to have the same magnitude. Well, that's interesting. What gets more interesting is, again, what is the difference? So if you just look at the dimensions, because, this one. So for a spring constant, it's mass divided by time squared. Cool. What's this? This is energy. And again, mass times, well, this is essentially c squared. Why? Because a length divided by a time is a speed. And if we're talking about a minimum of length divided by a minimum of time, that should give us a maximum of speed. The speed of light. It's squared here. Okay. So if you can see already, there's going to be a very particular difference there. And that difference is going to be 1 meter squared. So our reference length squared. Huh. That's interesting. Okay. So that's what we got there. And that's why it's, okay, I'm conjecturing things. I'm willing to put out there some bold claims, if you would, about what may or may not be going on now. Is it true? I just find it interesting that certain numbers seem to line up and especially if we happen to take this number here. So let's go back here, and we'll take that mass energy thingy. Okay, so we'll do this. So we've got certain other things here. So we got that. Let's do the Planck pressure. Under pressure. Okay. So it's defined as that, the speed of the light to the 7th divided by the Newtonian gravitational constant squared divided by h bar, blah, blah, blah. Okay. This ginormous number. It's like 10 to the 113 pascals, aka the unit of pressure. All right. So this also is, and I know Dr. Hassenfelder will disagree. Some people will say the biggest miscalculation within physics is, all right, so if we're trying to figure out what the pressure or the vacuum energy density is, some people are like, all right, well, we got to add up all these wavelengths. If we can go forever, it's going to be infinity or something. Long story short is the difference between this and the vacuum energy density. Vacuum energy density is, let's just do it. Universe vacuum energy density. Okay. So what is it? All right. So it's 10 to the minus 10. All right. So 10 to the minus 10-ish, 10 to the 113-ish, that's where we get about that 122 or 123 order of magnitude disagreement. And again, Dr. Hasselfelder would say it's like, well, that wasn't necessarily a prediction or stuff like that. I think the claim was it was a naturalness argument in that, well, what should the minimum of pressure should be? It's like, well, we'll just use Planck units because you see this. We have our units there, mass, length, and time. So we just do Planck mass divided by the Planck length, and then Planck time squared. Okay. Oh, look, we get the same number. It is the Planck pressure right there. So, but here's the thing. We're using a maximum, I claim, unit of mass. We're using a minimum of length, and then a minimum of time. And it gives us a ginormous number. So I'm just saying, if we're gonna claim that the quote-unquote vacuum of empty space is going to have higher pressure than we do on Earth, because what is it? The pressure on Earth is, what is it? Pressure on Earth. I think it's Earth atmospheric pressure. All right. So how many pascals? All right. We got about 100,000 pascals. That's pretty big. That doesn't have 113 zeros after it. So it's why would we ever assume that the pressure within quote unquote the vacuum, which is no true vacuum, would be more than we have here? That seems kind of weird. Okay. So that ginormous number there, why am I showing you all this? Because if we happen to take this number and we were to happen to, I don't know, divide it into that mass energy bank of universe, what do we get? Oh, looky. Those are the beginning digits and the exponential power of the Planck length. That's interesting, but it's something different. How do we get to this 10 to the minus 35 in cubic meters? Well, if we did the Planck length and biggin, we get this thing here, we've got this number, and then guess what we have to multiply it by to get that number we got? Oh, look, meters squared. Huh, that's interesting. Now, again, this might be all trivial and everything, but we seem to be getting the same digits in meters squared. And then the interesting thing is if we do that, that's a volume here, because it's cubic. So a single length and one dimension of length, it's kind of like a string or something like that. If you had 2 dimensions, it's kind of going to be a square. It's going to be like a flat surface or something. And then when you got it cubed, well, you got a volume, literally a cube. All right. So what happens if we were to, I don't know, let's take the cube root of that. Because we got 3 dimensions of length. Let's get it down to 1. So we just raise it to the 1/3. All right, see? We got that little 3 in there in our little radical thing. And then we get this length here. 10 to the minus 12 meters. What the heck is that? I don't know what that is. Good thing I don't need to know what it is, because Wolfram Alpha can tell me. All right. So approximations. You've got this. So let's click on this. Give us. All right. So about 3 times the distance between atomic nuclei and a white dwarf. Yada yada yada. Oh look. It seems to be just a little bigger than the Compton wavelength of an electron. Oh, that's interesting. That's sounding a lot like a primordial atom, if you would. So, if we were to take the limit of energy, according to this, the claim is if you took the limit of energy and you divide it by the maximum pressure, you're going to get down to a radius, or basically a volume of approximately a little larger than an electron. Don't that just beat all? Okay. Now the thing is, we can go back here. All right, so let's go. Okay, this guy. So let's take this out. Let's take out the c squared, because pressure, maybe that's kind of confusing. Let's just do our number so we can just get mass. How much mass do we claim is in the universe? The claim is it's this much mass, or at least in our mass bank. I'm moving aside potential field configurations. I could account for a lot more and everything, but this is just a nice, easy number to work with. Why? Because if also we take that number, so we got mass. So what happens if we were to take all the claimed mass stuff in universe and we were to crunch it down under the maximum density? Let's get it as dense as we could. How would we do that? Well, we would just do you guessed it, the Planck density. We just write that in there. Here's the definition here. That's this ginormous number, 10 to the 96 kilograms mass density. Okay, and again, it's literally Planck mass divided by the Planck length cubed. Okay, that's what this stuff is telling us. Okay, so just feel free to trust but verify. Planck mass divided by the Planck length. Yeah, I can spell. I swear I can spell cubed. All right. There we go. Okay, so Planck mass density. So let's just take that and let's divide it into that ginormous number we had. Boom. Oh, look. We're getting the same answer, because the difference between the Planck density and the Planck pressure is literally c squared. Because, well, that's what it is. We just take that, we multiply it by the speed of light squared, and then we get the Planck pressure. Under pressure, cool. And again, we're getting the same. Divide by that. We're getting the same number as if we divided that 7 times 10 to the 78 number by the Planck pressure. Except we're doing density, because we're talking about mass here. All right. And that would also give us roughly the radius of an electron when we do the same thing and we raise it to the 1/3 power, which is the same as taking the cubed root. If you raise it to 1/2, you're going to take the square root. Bada boom, bada bang, back to about the Compton wavelength of an electron. Okay. Now, I did those calculations, and I'm like, oh, that's interesting. That actually seems to line up with a lot of what many people have been saying. So, I mean, that's kind of cool. So, again, you don't have to believe anything else within the model. You don't have to believe in, the hyperbolic figure 8 knots complement is essentially helping stitch reality together itself and is allowing for all these other things. You don't have to do any of that stuff. You can just be like, well, maybe, just maybe, if we were to assume maximal extendability and there happen to be some minimums that we know of, like the Planck length and the Planck time, maybe we could use that to logically construct what the limit might be. So I was saying maximum before, but you have to be kind of careful with that. So Now, there might be better language for this, but that's why I put number 1, universe, lower U universe, because, well, if you're to use big U, that would basically, if you're going to claim that there is a limit to something within the universe, you're going to run into the container problem. So it's like, what box does that fit in? People say like, oh, that's a terrible question. It's like, really? Isn't that the first question that everybody has when you say it's like saying that's not an appropriate question? Really? Come on. That's my take there. And again, I could be completely wrong, but ultimately, who knows? Maybe it's like in Men in Black, where at the end there, they have the galaxy, and then there's just a whole bunch of ginormous space aliens, and they're just playing marbles with us or something. Could it be something like that? Maybe. I don't know. But at least for the sake of this argument, the claim is we have 5 Platonic dimensions of measure. Now, I'm using the word Platonic because, number 1, well, there are 5 Platonic solids. And at least from these 5 dimensions of measure, we can reconstruct the constants of nature. Now, occasionally you'll see something like an angle, but then you realize it's like, well, angle doesn't really have a meaning unless you're comparing like different lengths and stuff like that. So that's kind of where that comes up with there. So what we're doing is, if there happen to be minimums, so if you get a Planck length, that's a minimum of length. All right, so what happens if we compared it to our reference of length within a coherent system of units? And we do some of these calculations, and literally that's what we did all over here. Basically all these guys, we have, the claim is, if we have a dimension of length, the base of length, which in this case happens to be a minimum as far as we know, it's the Planck length, it's about 10 to the minus 35 meters. All right, so the limit would be, literally, I'm basically just doing this, it's meters squared over the Planck length. So basically, we're doing that same thing, and we get about a potential radius of the universe. Maximally, the limit would be about 10 to the 34 meters. Now, personally, ontologically, so basically what my thought process is, personally, for how this might work is, once we reach that, we might actually persist. Now, again, I could be completely wrong on that. Maybe this is a limit. Once we get there, maybe there's going to be a big rip. I don't know. Maybe after that, we start going back and there's going to be a big crunch. And again, this is just a particular framework that if you happen to be doing some calculations and everything, it's less than infinity. So that makes it a little bit easier to go around and do some calculations for. And who knows, maybe it's infinite. I don't know. Again, there is one infinity on here. And again, this is not necessarily from calculation. This is utilizing what I've learned from Thad, and I happen to be a subscriber to the HF8 model, or the minimal arena, if you would, in that, like, once you get something that can persist, we will continue to persist. Now, the exact layout and form may change, but that's basically, this is a personal opinion here. Again, could be totally wrong. But again, we have other things here. So again, mass, that's our base is the Planck mass. That's about 10 to the minus 8 kilograms. And then if we did that whole thing where we did that, this ratio of meters divided by the Planck length, and we square it, we get a maximum here. So that's where we get that 10 to the 61 kilogram number. And then time is an interesting thing, because we do the same thing, we get about 10 to the 26 seconds. What the heck is that? So right now, estimated age of the universe when we rewind general relativity and stuff is about, giga years? It's 10 to the 9, about 10 to the 10 seconds. So if we did about 10 to the 10 seconds, that's about 16 orders of magnitude greater than that. So what happens is that when our time runs out, okay, so within years, normally we estimate universe as we know it is about, it's about 13.7, about 14, call it 14-ish billion years old. Okay, very old. All right, this is a lot more. This is about 16 orders of magnitude. So that's about, what is that? It's about 1,000,000 billion, something like that, times longer. Okay. There are some other interesting calculations we can get into at another time. But right now, I really want to kind of stress that, the mass energy of our realm seems to line up with the Planck spring constant. Now again, I've never heard the term Planck spring constant, but if you do the calculations in Planck units, and you're getting something that comes out that's telling you something that seems to be fundamental, at least within calculations within most all of physics, maybe it's something we should pay attention to. And ultimately, that's the big thing, because even if you do a Google search of this number, you might find like a math problem that has something like this, section, blah, blah, blah. I haven't seen anything. Then again, that was a very cursory search. But something about a mass or its mass energy equivalent being the same number of digits and magnitude of something, those are the things that make you go, or at least for me it does. Okay, let's finish going back, and then we can get to the folks that have joined us in the chat that I've been horribly ignoring after I boomered this string twice. Again, thank you to Poindexter for pointing out that, after I fixed my audio, it still wasn't fixed, and I was still boomering out. Apparently now we're 5 by 5, yes. Technology is great as long as it works. Okay. And then charge, basically, claim is the basic charge is the Planck charge. And if you were to multiply that by that 10 to the 69 number, you're going to get this amount of coulombs. All right, 10 to the 51. Massive amount of charge. But if that's massive amount of charge spread throughout the universe as we know it, might make a little bit more sense. And then we got temperature, which as far as we know, the Planck temperature is a maximum of temperature. Here, I'm claiming it's a base. How the heck am I claiming it's a base? Well, if you took this number right here and you divided it by the Planck pressure, well, as you're constraining things, if it was just heat and you had to cram it down to the size of about an electron, it's going to be about the Planck pressure, aka if that was let's go with the standard terminology of what different folks have proposed, a primordial atom, if you would, so to speak. That would basically be an initial state per Planck volume. You're going to have a Planck temperature per Planck volume, a Planck charge per Planck volume, basically you're going to have the equivalent between these things, because these things are essentially ones within a system. Now, the Planck temperature seems to be really weird because it's absolutely ginormous, and it's the only one that, at least according to our coherent system of units, actually has a positive number. So at least this could be a reason why, because if we're going to claim it's a base, if we were to happen to have a quote-unquote starting state, basically that's about as far as I can actually do the calculations back. I can get about down to the size of an electron for the total mass energy bank of universe I claim. Okay. And then we have these limits here, and that limit doesn't really make sense because for temperature 10 to the 101 Kelvin, this is a limit. You can't get past that. Yeah, but when you multiply it by Boltzmann's constant, you end up getting the same number here. Okay. Hence, these are ones within the system itself. Okay. Initial rambling and rant over. Okay, so, all right, we started, it took me about 10 minutes to actually correct things after Poindexter pointed them out, so we're about halfway through. All right, let's go back. All right, so Poindexter's commenting, one can argue entropy is lower now than immediately after the big. See, this is a very interesting thing. Let me get the shades a little bit before too much radiant energy gets my laptop to overheat. Okay, but so people seem to disagree about this. And again, I'm not a general relativity expert. I can do a few calculations to match some data pretty well, but I'm really just a monkey with a magic typewriter and an idea of maybe where to look. So it's interesting because it's like, well, entropy, what is that? I think somebody told Boltzmann or something like that. It's like, Well, this seems to be about the same calculation for this. Just call it entropy. Why? Because nobody knows what that means. It's like, it doesn't really seem like a good reason. But my general understanding is it's a measure of disorder or our lack of knowledge about what might be going on. Okay. Now, if you're in an extremely hot, dense state, I don't know. That kind of seems like things are going to be kind of the same. But then again, it's like, well, is it kind of the same, or is it so energetic that it's so crazy? There are also folks that will say that, well, entropy will always increase, or that's generally the second law of thermodynamics. It's entropy tends to increase, and that maybe it goes down a little bit for a while, but overall, it's going to potentially go up. Is that the case? Heck, who knows? Maybe entropy is technically, depending on how you want to measure it, maybe it is constant. And we're just going through different forms because, well, right now we can't measure all of the universe. Or at least I would claim our observable universe is about 10 to the 26 meters. And at least according to this guy over here, our first thing is if our maximally extended radius, according to this, would be about 10 to the 34 meters. So that's about 100 million times larger. So maybe hypothetically we could at some point. Can't necessarily say, but hey, welcome some person. Good to see you. Oh, DJ, yeah, I know DJ Ronnie G. I see him in the chats around and everything. Oh, I didn't know he did science. Huh. See, maybe I should pay attention to the chats more. This is where you learn things and you run into different folks. So Poindexter's talking about Maxwell's demon. So Maxwell's demon is, okay, that's kind of like that thought experiment to kind of go over, whereas it's like, all right, so how could we try to do this? How could we try to break the laws of thermodynamics? So the whole thought process is, all right, you got a box of gas. It's got one side, it's really hot. The other side, it's really cold. Okay, if you were to have an all-knowing, all-powerful demon that was just looking, it could see the hot particles, or normally if you have, excuse me, I need to restate this. You have a hot box, you have a cold box, and there's a little door between them, okay? Normally if you just open that door, eventually they're gonna balance out and you're gonna have the same temperature. But if you happen to have two things, and if it was the same temperature, what if the demon was looking and being like, that's a very energetic particle, and it opens up that little window and only lets that particle through. Eventually you could have more hot stuff on one side than the other. The problem you run into, it's like, okay, how is the demon doing that? Well, it has to open the door, so it has to use some energy. And then I think ultimately, from what I recall, and again, I could be totally wrong here, is that even if you assume all the idealized things, it's when the demon needs to erase memory. So when the demon needs to forget things, that ends up being the unaccounted for energy, so you end up needing to have energy for the system. It's something like that. I probably butchered that, but that's the general gist of stuff. Some person's saying that we need a bunch of science props, globes, skeletons, Tesla coils. I mean, that would be really cool. I mean, hey, feel free to support the Physics Monastery if you want. Maybe we could get some more cool stuff. We've got, I think the fanciest thing we got is this guy over here, which is, all right, so this one is a 3D printed thing from the hyperbolic figure 8 knot that Professor Henry Segerman had done the code for and everything. So yes, we can. You can kind of, yeah. You can see the knot in there. And hold on. See, there's a little knot, and yes, we still have all the stuff here because this is very fragile, and we kind of already broke the other one. So that's kind of the thing. Ooh, actually, it's kind of cool in the light. All right. So where are we going? Hey, Keishal. Good to see you. Thank you for joining, my friends. Sun King. Well, listen, I don't know. Again, a lot of this, it might just all be trivial just because we're multiplying it by the same thingies and stuff. And if these are ones within our system, I mean, well, we would also kind of assume that this might be the case, But then again, it's like, now, is that interesting? Was that expected? Might this be telling us something? I don't know, but I'm making the assumption, or at least the point I'm kind of trying to hammer home, is that once you have a coherent set of units, we're going to get ratios. As Julian Barbero said, nothing but ratios is what he wants on his tombstone. Okay, so if there's nothing but ratios, let's take a ratio. Let's take a ratio, play around, see if it can tell us something. And apparently, according to these calculations, maybe it is telling us something. When you get certain things to align, it's kind of... See, I don't know. And again, science is more... It was more of my safe space. And again, not formally trained in the traditional sense by going to all these different things. So number one, I don't know any better. So again, maybe there are absolutely fatal flaws that I'm completely missing. I don't know what's going on, but at the same time, if I don't know any better and somebody hasn't told me that you can't do this, well, maybe I try to do it because it's, well, I don't know. You get enough folks saying it's like, you can't calculate the mass of the Higgs boson. It's like, all right, I don't really care because, well, at the same time, I also heard folks, a lot of it's just Thad setting the example of, it's like, I hear folks saying, you can't calculate the fine structure constant. And Thad has, hold on, he does this little equation that, oh, look, once we subtract out the magnitude of the Planck mass, it's almost like we're subtracting out a mass gap, perhaps, that this has good agreement to all the known digits of the fine structure constant. Now, there's some additional ones once you get to past about 10 or so that people can argue about, and there's about a 7 sigma tension between the Berkeley measurement, I think was it the MIT or Harvard measurement that they had more recently that they're basing the most updated thing on. Okay, maybe this is wrong. Maybe the new measurements are right. Okay, what does this need to be modified to fit the new measurements? Just divide this by the square root of 2. That seems to also come up in quantum mechanics. Root 2 is a very powerful thing. Why? The Pythagorean theorem. Okay. So, that's actually a good idea. You know what? On Henry Segerman's channel, they kind of did that. They did some of the 3D printed things, and then you just kind of like put a light or something in it. And it does look really cool. So, as Poindexter is saying that, so the demon receives information just as a life is an information construct in its closest. My brain's a little fried from a bunch of stuff and thinking earlier, and probably a little bit of lack of sleep. That sounds like perhaps it could be plausible, because ultimately what I remember is, okay, number one, if you grant the demon, the demon can just magically open the door. Because once you're starting to do that and you're trying to determine things, I'm like, okay, now you're putting energy in the system because you're trying to separate the demon from the system. But if it's part of the system, even if it was outside the system, apparently the ability to erase its memory seemed to be one of the things that I think there was either a mathematical conjecture or perhaps a proof for. I'm gonna caveat it's probably not a proof, because proof within mathematics is, this is true within mathematics. Okay. So where were we going from here? Okay. So if we happen to have, where should we go? Let's see. So we covered the Planck spring constant. Let's go through, where do we want to go? Let me hydrate and let's play a quick Wolfram clip while I figure out where we should go. Let's see, is there anything else? Maybe we should learn a little bit.
I should learn all these memes.
I should have played more than a 1 second clip. So let's play a 2 second clip.
You finally flipped.
That's where we can go. Thank you, General Brewer. You and your rambunctious nature actually gave me an idea. Okay. Am I aware of the pattern in randomly generated prime numbers? I was gonna say it's like I think it's hard enough to find patterns in prime numbers. I think what was it? Who is it? Kurt Mungle. Shout out to Kurt. He interviewed a gentleman. I think he was a former string theorist. I think he's a mathematician. But one of the things he's doing, he's working with a lot of the large language models like ChatGPT, Claude, and stuff to try to see if they can recognize different patterns and basically help do like next level mathematics, if you would. And apparently they found interesting things. I was just listening to, I think, the first half hour of it earlier. And I think if you have any links or anything or more information, Poindexter, please let me know. But as far as I know, he said that at least a lot of the large language models weren't able to find proofs. Oh, actually, hold on, let me see. Pattern in a randomly generated primes. Okay, prime numbers near to each other tend to avoid repeating their last digits. Huh. That's interesting. Let's take a look at this. While primes are often considered randomly distributed, recent research reveals a subtle pattern in their distribution. Primes are not as randomly distributed as previously thought, and they tend to avoid repeating the same last digit. This means a prime ending in a certain digit is less likely to be followed by another prime ending in the same digit. What the heck is this picture? Ooh, that's pretty. What is... Oh my god! What is this? Let's visit. Where is this? Oh, it's from Medium. Okay. Let's see. All right. From our pattern, stable interviews of 10, 20, and multiples. What? There's a base 10 pattern in primes? No. Okay, we're reading this. Sorry. This is fascinating. All right. So this is from Maria Folming. So this was from last year. Prime numbers have been a fundamental focus in mathematics for centuries. Euclid proved their infinitude over 2,000 years ago. The challenge with prime numbers is predicting their distribution. There's actually a clear pattern in the distribution of prime numbers. This pattern solves one of the oldest mysteries in number theory. The pattern connects the field of mathematics, physics, chemistry, and astronomy. I feel like, did I hear about this and I just glossed over it because I thought it was just another one of those standard clickbait things where it's like, you see the thing. I think I'm stealing this meme from Floathead Physics. It's like, you'll see the headline and it's like, physicists achieved the ancient goal of alchemy by turning lead into gold. And then you go a little deeper into what it is. It's like, yeah, some physicists collided a bunch of ions and stuff together, create about 27 nanograms of gold that end up dissipating after like a few milliseconds or something. Okay. The headline might be technically true, but if you're thinking like the whole Newton, it's like, all right, we're going to take this hunk of lead, we're going to do some stuff and things to it, and that hunk of lead's going to turn into a hunk of gold, and we're going to be set because now we can create gold, not even considering the fact that if we can turn lead into gold, the price of gold's probably going to plummet. I digress. But, yeah, I think I viewed it as kind of one of those clickbaity things. But, here's the thing, Poindexter. I can't say that. I want to say that. I'm very sympathetic that the universe has a grid that everything snaps to. I'm very sympathetic, but I try to follow where the data leads us, where the calculations lead us, because I could say those words, but I don't really have evidence. That's kind of the whole point of this. I'm trying to amass evidence, kind of like being an attorney, and I'm not an attorney. That was my dad, Mr. Memes. God rest his soul. But I'm trying to build evidence for a case to make the case for a particular model. And again, we're following a coherent framework here. So utilizing the coherent framework of SI and the units that we have along with the hard-won measurements. Basically, the data that we have now, like the data that's in like Wolfram Alpha, like literally we've got works from like back to Euclid in ancient Greece, stuff from like ancient like Mesopotamia, China, like the European stuff, and like all this other knowledge from all across the world, from humanity, from literally millennia after millennia of human hard work. We've been able to figure a lot of stuff out. So I think this is like a little pat on the back to humanity that we've been able to get this far. So if we're trying to take it to the next level, if you would, the claim is certain patterns, perhaps they can guide our path, or at least utilizing a coherent system. And at least here, the claim is that we're literally using like nothing but ratios. We're saying that if there happen to be some minimum things, perhaps we could take those minimal things, and if we invert them, we would get maximal things. And by basically just doing that, and then, squaring it, we get some very interesting numbers that seem to line up that might be able to explain what is going on. So let's see where we're at. Okay, let's go back to this prime article because it's totally fascinating. All right, the system. The system is a circle divided into 9 equal sectors. From the center of the circle, we place natural numbers in order starting with 1 in a spiral shape, expanding from the center to the periphery. The transition to another orbit for all natural numbers will occur at the boundary between sections 9 and 1, shown at the red line. So basically, this red line here, between 9 and 1. Okay. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what is going on here? So 1. Okay, so they've got these numbers here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so we're going up. Okay, so what is it? What is it saying? So we mark the prime numbers in the picture. We see that the 3 sectors of the circle do not contain any prime numbers. These parts are 3, 6, and 9. Well, 3 is a prime number, and then the others aren't. Oh, are they just saying within those sections? Let's see. Okay, so 3 is there. So once you get past the first prime, there are no others. Oh, that's interesting. Okay, these sections contain only composite numbers. Primes will never appear in them to infinity. The only exception is the number 3. And as we know, Nikola Tesla had a deep interest in the numbers 3, 6, and 9. I think we may have covered that at one point. So 3 is the only number, it's the only prime that pops up, and there are no other ones there. How very interesting. That gets my noggin a jogging the spirals. All right, we divide all prime numbers into 4 groups. A prime number that ends in 1, the pink line, blah, blah, blah. And ones are there. Okay, so 1, 3, 7, and 9. So we got, hold on. So 1, 3, 7, and 9. So 1, 3, 7, 9. Okay, so 1, 2, 3, 4, 5, 6. Okay, so there's 6 places where the primes start coming up. That's interesting. Okay, so 3, 6, and 9. Is that what it is? No, that's 2. Oh, no, that is 3. That is 3. Okay. So 3, 6, and 9, aside from 3. Oh, I see what they're saying. I misread that. Okay, so there's no primes along there. Oh, in each of these categories, prime numbers are arranged precisely along the turns of an equilateral spiral. There are a total of 4 spirals where the prime numbers appear. Each group of prime numbers is expected to continue generating in the same manner towards infinity, following their respective spiral paths. Okay, so they're expected. So as far as we know, does it resemble the cosmic web, the large-scale structure of the universe? I mean, those are pretty spirals. I mean, I would love to have something like that be true. I can't say that, but twin primes, pairs of primes that differ by 2, serve as connecting bridges over sections 3, 6, and 9. Oh, okay. So, what's that, 157, that's 59. Where, oh, blues are primes, okay. 183. Okay, I don't see that. Oh, of course, they needed to add the extra stuff in. All right, blah, blah, blah. Connecting bridges. The bridge also connect neighboring spirals to each other. Okay. Oh my God, this is even kind of like a hypergraph. I feel like some of this stuff was probably done with Mathematica, and if it wasn't, maybe it should. Okay. How are primes distributed along the spirals? They seem to be irregular, but there is a pattern in this irregularity. When the difference between them is 10, they will always connect the circle section 1 with 2, section 4 with 5, section 7 with 8. Examples are 7, 17, 13. Oh, wait a second. Oh, so when there's a difference of 10 or mod 10. Huh. I have not heard about this before. This is really cool. When the difference is 20, you will always connect the circle sections 2 with 4, 5 with 7, and 8 with 1. See, the prime numbers jump over the yellow sections since there are no primes there. It will never be. Oh, has that been proven? Well, I mean, okay, so if it's a multiple of 9, okay. Well, if it's a multiple of 9, then okay, that makes sense. Multiple of 3, once you get past 3, okay, that makes sense. Huh. That is... because we're going 9, so it's mod. So, okay, so the 4 is... Because normally an even number aside from 2 is not prime. Huh. Whoa. This is like a record that's been disjointed and stuff like that. Huh. The intervals, all 4 groups of primes, are organized uniformly along their spirals. The stable distances between primes is 10 and 20. Let's call them basic intervals. Apart from these stable distances, there are constant intervals on the spirals, 30, 40, 50, it's seldom. Okay, the smallest interval is always 10. Huh. Are we touching into some of the unreasonable effectiveness of the number 10? I mean, I'm not gonna lie, I'm very, very biased towards this, because occasionally there's some calculations. You look at this like, there's no way that like 10 could be built into reality. I mean, what are you gonna say? It's like, I don't know, we got like a double cover of 5 dimensions, so that's a reason why we have 10. I mean, I would love for that to be the case, but listen, as somebody that does a lot of numerology that goes nowhere, I feel like I'm grasping for straws. But if there's something to this, this seems like a much more mathematically concrete reason. Ooh. So the jumps are always of 10. The interval green lines, okay. High resolution pictures zooming in. Oh, it's available for download. Okay, so they're saying the interval of 10 here, interval of 20, interval of 10, interval of 20. Okay. So go back 4, more stuff there. Sustainability of the system. All natural numbers in each section of the circle follow one principle, from the center to the periphery. All the last digits decrease in order while all the basic digits increase in. Oh, that's cool. Okay, see over here, you see, it's 181, 172, so we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5. And then we're starting off, all right, so 1. Okay, so 1, 10, 1, 2, 3, 4, 5, 6, 7. Oh. And then you got a couple of 10s repeating. Oh, this is really neat. Oh my God. Thank you, Poindexter. I had no idea this was a thing. This is very cool. Okay, so what are they saying here? Connecting math, physics, chemistry, and astronomy. The graphical visualization demonstrates a principle of how prime numbers are distributed. Prime numbers are organized and behave in ways that mirror electrons in an atom. They are arranged in orbitals around the nucleus. The nucleus is the starting point of natural number in the center of the interval just between primes and the spiral that can be compared to, okay, that seems a little tenuous there. The discrete steps, electrons, okay, I think that's, we're leading into it a little bit more, but wow, that is really cool. Dang. See, this is the power of the internet. This is how I claim the internet is working as intended. Why? Well, I didn't know that before we started. I was just rambling on, trying to make a case, and then all of a sudden it's like, oh look, this appears to be a thing built into reality via the primes. What are the primes? The primes happen to be some things that are literally, by definition, indivisible, except by themselves in one. I know Rick has pointed that out as well, so this is really frickin' sweet. Okay. Dang. But, alright, so after reading all that and going on for our requisite hour, so I think that's about all the juice I have in me right now. But, listen, man, all I do is, it's mostly using Wolfram Alpha. I'm still trying to work up my programming skills to actually be able to program useful things. We'll see. It's just practice. That's all it is. So, listen, if you get better at playing Smash Brothers or Mario Kart, well, usually because you play it more. I just view it like a video game. If you're playing something more and you get used to it and you get some tips from some other smart people that can help you, you're going to improve. Why? Well, that's the story of humanity. I would claim to level up. I'm not wearing the shirt. It's over there, but we'll get there. Hey, Lug. Good to see you, my friend. We were just looking at some very pretty pictures with prime numbers, and apparently there exist certain patterns that I didn't know about until Poindexter told me. So, but we're wrapping up for right now. So other than that, hey, thank you all for joining. Take care of yourself. It's a wacky and wild world out there, but let's do it better tomorrow. Peace out.